In today's video, we are going to discuss two models that describe the electrons in the atom. And we're going to take that and move on and describe the um, organization of the periodic table. And the model we're going to use is a model that is going to explain why some atoms, like helium, for example, are inert, whereas in contrast to that, atoms like hydrogen are so reactive. Okay. Now, for example, hydrogen exists as a diatomic molecule because it's very reactive. So you get two hydrogen atoms combined together to form a molecule. So what's about them that makes them so reactive? And are there other elements as reactive as hydrogen? And that reactivity is actually extended to group 1 element, like lithium, sodium, all of them are very reactive. And as we will see that there is a periodic law that sums up all these observations, like why elements in group 1 are very reactive, whereas elements in the noble gas column are inert, like argon and neon and helium and so on and so forth. All right, so we're going to look at these models in here. We're going to look at two models, the Bohr model and the quantum mechanical model, that will help us understand the behavior of these elements. All right, and basically we all know that the electrons are responsible for reactivity. Therefore, we are going to look at where those electrons are and how are they going to affect chemical and physical properties of these elements. Now you notice we said two models, Bohr and quantum mechanical model. So why do we need the quantum mechanical model? The quantum mechanical model is a model that actually reshaped the 20th century. It actually changed the way we look at the world. And up to that point, classical mechanics was used to explain everything. Okay, when we say classical mechanics, we're looking at the laws that were proposed by Newton and others, and Maxwell equations that described electromagnetism. So Newton described the behavior of matter, whereas Maxwell equations describe the behavior of energy. Together, they gave us classical physics or classical mechanics. Unfortunately, those can explain very well the world at large, things that we can see, right? But when it comes to stuff that we can't see, like electrons, that are incredibly small, then unfortunately, their behavior is undeterministic. So when we think of classical mechanics is very deterministic, right? That's the key word right there. So if we know A and B, we can predict C. Unfortunately, when it comes to electron, their behavior is completely enigma. And so, for example, directly observing an electron in an atom is impossible. So you need something else, and that something else is quantum mechanics. All right? It's a way to explain the submicroscopic world. And the work we're going to look at, it was done by many famous physicists that discovered that behavior, all right, such as Albert Einstein, Niels Bohr, Max Planck, Heisenberg, Schrodinger, and so on and so forth. In order for us to understand this, first I'm going to take you through some of the problems that existed at the end of the 19th century and the turn of the 20th century and what led to the development of quantum mechanics. And in order for us to understand that, we need to understand what's electromagnetic radiation. So I'm going to start with that, then we'll move on to some of these problems. And the reason we're going to go into describing what electromagnetic radiation, because it was the tool that was used in order to understand the behavior of electrons in an atom. Using electromagnetic radiation, which light is part of electromagnetic radiation, is a form of electromagnetic radiation, then the electron did respond to simply shine in a light on it. So that was the go-to tool that was used to understand this. So when we talk about electromagnetic radiation, we are describing the way energy travels in space. And energy travel in space in a form of propagation, which we call a wave, okay? A way that repeats itself. Okay, so let's take a look at some of the properties of light, which we can expand to all electromagnetic radiation. So like I said, it travels in the form of a wave. And when we say wave, we're talking about something that keeps repeating itself. It propagates. So if we take a look at the following wave right here, we see that it repeats itself as it goes through the following, right? So it goes through this part right here, goes up, then it goes back down, back up again. So if we were to look at the part in which that wave completely repeats itself, okay? It goes from this point right here all the way to this point right here, all the way to this point right here. So this will give us a complete cycle. That's what describes the nature of the wave, the identity of the wave. How much space does it cover before it repeats itself again? We call that the wavelength. And that is given that Greek letter lambda, okay? So it's given lambda, which is the distance between two consecutive points in order for it to repeat itself, right? And since it's a measure of length, then the SI unit is meter. But since we're talking about stuff that is very small here, so we're going to use nanometer as the go-to unit. Another way we can describe the wave, instead of looking at the distance at which it covers, we can take a fixed point in space and count how many wavelengths actually pass through that fixed point in space. And we choose a unit of time. Since the SI unit of time is second, we count how many of those pass per second. We call that the frequency. Okay, so it's the number of waves that pass through a certain point over a unit of time, which is frequency. So we're gonna call, the units are going to be cycles per second or hertz. Wavelength and frequency are related, and we'll see how they're related. But before I move on, I want to describe one more unit, but that does not tell us about the nature of the wave, but rather the quantity, not quality, but the quantity, how much of that wave I have. We call that the amplitude. So if you take many waves and add them together, you get a higher amplitude. So we either call it amplitude or we call it the intensity. So we can call this intensity as well. All right, it's the amplitude or the intensity. But let me go back to wavelength and frequency and see how they're related. So if I were to take a wave that has the following wavelength, lambda, within a second, we can have 1, 2, 3, 4 waves in a second. So 4 waves pass through a fixed point in space per second. That gives me a frequency of 4 cycles per second, or 4 hertz. If I were to take that same wave and cut it by half, the wavelength, okay, divide that wavelength by half, now I have a shorter wave, then I can fit 8 cycles per second, right? And if I were to take a quarter of the original wavelength, I can fit, right, 8 times as much, so 4 times as much if I cut it by 4, right? 4 times as much, so that will give me 16 cycles per second. So we can see that wavelength and frequency, again, let me repeat this, wavelength, we give it the Greek letter lambda, whereas frequency, we give it the Greek letter nu. Wavelength and frequency are inversely proportional. But there's another factor that they're related by, and that would be how fast does the wave go through, not just the wavelength, but how fast it goes through. So we can combine the two, wavelength and frequency, so the speed at which light travels. The speed of light is around 3 times 10 to the 8 meter per second. And we can relate the two. The speed of light equals frequency times the wavelength. Let's take a look at an example how we can use that information. Calculate the wavelength of a radio signal with a frequency of 100.7 megahertz. So we're given the frequency to be 100.7 megahertz. I want to find the wavelength. So I'm going to go from frequency to wavelength. That means I'm going to use C equals nu times lambda, but I need the units to be consistent. So I'm going to convert my units frequency from megahertz to hertz. All right, then I will use C equals lambda times nu, rearrange that equation to isolate lambda on one side, and that will be C, the speed of light, over nu. So step one, let's convert from megahertz to hertz. I have 10 to the 6 hertz in 1 megahertz, which 1 hertz is equivalent to per second as well. So we can do that. Then lambda equal the speed of light over frequency. That would be 3 times 10 to the 8 meter per second over 1.007 times 10 to the 8 per second. I get 2.98 meters. All right, that's how the two are connected. Now, as I said, the wavelength determines the nature, the identity of whatever electromagnetic radiation we're looking at. And we also said that light is a form of electromagnetic radiation, right? And when we say light, we're talking about the visible spectrum, the stuff our eyes can process and can see. And we know there are many different colors, right? We're used to white light, but white light is actually a component, has many components, and it's made out of mixtures of colors. That's the visible light. It's made out of red, orange, yellow, green, blue, indigo, and violet. You need to know the sequence of these. So if I were to pass these, if I pass it through a prism, it will separate like this. The same is true when you see color. Actually, what you see is the reflection. So if we look at this girl right here wearing a red shirt, the reason we see that red shirt is because that shirt absorbs all the color from that visible spectrum except red. That red reflects back at us and we can see it. But visible spectrum is only a small part of the electromagnetic spectrum. That's the visible light. I need you to know the actual boundaries of that spectrum. It has red at 750 nanometer to violet at 400 nanometers. Those are the boundaries. You should know those boundaries of the visible spectrum as well as the sequence of that spectrum. All right. In addition, what I need you to know are the other regions in the electromagnetic spectrum. And we're going to start left, low energy or frequency, and right, we're going to have high energy or frequency. All right, that's high on the right, low on the left. So we're going to start with low energy, and that would be radio waves. Those have the lowest energy, followed by microwaves, followed by infrared. Infrared is followed by red. Then we go through the visible spectrum. Then you go to ultraviolet, followed by X-ray, and the highest electromagnetic radiation in terms of energy are gamma rays. Okay, those are gamma rays. You should know the sequence of these things. So you're responsible of memorizing the sequence. So it can ask you a question like this. Order the following type of electromagnetic radiation. I can ask you to order them by wavelength, frequency, or energy. I told you that frequency and energy are inversely proportional to the wavelength. That means the longer the wavelength, the lower the energy and frequency, and vice versa. So if I want to order them by wavelength, that means the short wavelength is going to be high energy. So I'm going to put them in high energy first. Highest energy among those are gamma rays, followed by UV, green light, red light, then microwaves. So we can come up with the following. Now, if I want to order them by frequency, the frequency is opposite, inverse to wavelength. So I'm going to start with microwaves all the way to gamma rays. And if I'm going to order them by energy, it'll be the same as frequency. All right. So that's some of the properties of light. But now I want to talk about the behavior of light so we can understand how it was used to come up with the quantum mechanical model. So when we talk about the behavior, I'm going to describe several phenomena of light. First is when we have two wavelength, or not wavelength, but two electromagnetic radiation interacting. We call that interaction interference. Okay, when two or more waves interact, we call it interference. They're gonna either interact in an additive manner, we call that constructive interference. You notice how these waves, in terms of their amplitude, it increases when they interact constructively. Or we can look at them where they interact destructively or subtractively when they're off phase. Notice how the crest here meets this bottom trough. So you notice those cancel out, these cancel out, and so on and so forth. So we end up with destructive interference. What does that mean? It means that if you have light and they're additive, you get brighter light. And if they interfere destructively, they cancel each other out. So you don't see anything. That's basically what we're talking about. Okay, that's one phenomena, interference. Now let's talk about another phenomena, which is called diffraction. I know we know light and we take it for granted now that light is an electromagnetic radiation, but it wasn't understood back in the days, right? So before the 19th century, very little was known about the nature of light. And it was a lot of back and forth about whether light is an electromagnetic radiation, is it a wave, or is it a particle? If it's a particle, if you take a particle and you shoot it at an obstacle with an opening, it should go through and you can only detect it right behind it. But if it's a wave, it would actually bend around that opening. That bending, known as diffraction, okay? This bending around an opening is called a diffraction. Traveling particles do not diffract. Electromagnetic radiation, or a wave, does. All right, so around 1800, Thomas Young performed an experiment known as the double slit experiment, where he would pass light through a slit with another obstacle behind it with two slits. If it was a particle, he shouldn't be able to detect anything on the following detector. But when he performed the experiment, he observed a diffraction and interference pattern. Okay, where you get those bright spots are constructive interference and the dark spots are destructive interference. So that experiment showed that light actually is an electromagnetic radiation. So notice right here we have two phenomena of light: diffraction and interference. And a third phenomena of light is something we call refraction. So when light passes from one medium into another, for example, outer space into outer atmosphere, you go from air into water. Those are two different mediums. So when light goes from one medium into another, its speed changes. That change in its speed causes the component of light to bend. That bending is called refraction. That's why, for example, when it rains, you'll see water droplets in the atmosphere. When light passes through those water droplets, it'll create a rainbow because it causes bending of the different components of white light. When light comes from the outer space and it hits our upper atmosphere, then the air in our atmosphere causes light to refract. The blue component of light bends the most out of it, and that's why our skies are blue. At sunset, red light bends the most, and that's why you can see red at sunset, and so on and so forth. Even when you have really a day where pollution is really high, or if there is a fire, because of all the components in the atmosphere, causes red light to bend the most, and you see the sky is red and so on and so forth. So this is known as refraction. So now that we understand all these behavior of light, then we can go and look at actually how this stuff was used in order to come up with the quantum mechanical model. All right, so at the turn of the 20th century, there was a phenomenon known as black body radiation. So when you heat objects, they glow. That was not understood, okay? But I'm not going to go too much into detail, just giving you a little bit of background. So when you heat stuff, let's say you heat it to 1,000 Kelvin, it would glow red. If you heat it further, it'll glow yellow. And if you heat it even further, it'll turn white. Now, according to Maxwell equation, classical physics, when you heat stuff, it should get more intense, not shift color, shift frequency. That frequency dependency could not be explained by classical physics. As a matter of fact, they tried to come up with many equations to explain this, but all of them failed, especially when it came to the ultraviolet region. And at the turn of the 20th century, they actually termed that the ultraviolet catastrophe. That physics failed to explain this. Then Max Planck proposed a solution to that problem. It was a very radical way of thinking. What he proposed is the following. He goes, if we think of light as we think of matter, for it to be discontinuous rather than being continuous, then we should be explaining this. Okay? So what does he mean by that? If you remember, before the discovery of the atom and so on and so forth, it was thought that matter was continuous. Then we discovered the atom. Then we discovered that the atom even have an inner core, right? A nucleus with protons and neutrons and electrons. So what Planck is proposing, that energy is behaving in a similar manner, that energy is quantized. Okay, so in order to explain that frequency dependency on the amount of energy, he goes, when matter absorbs energy, if the energy that is being absorbed is equal in its frequency to the electrons in matter, then those electrons will resonate at that frequency, and that's why we see different colors. And he proposed that that energy can be gained or lost, that's resonance in it, and a whole number multiple quantity, which have a frequency in it and a constant that he derived that we still use until today. Okay, that change in energy for a system can be described as follows. Planck's constant times the frequency of light multiplied by an integer. N is an integer, nu is the frequency. That right there is a small packet of energy, which he called a quantum. So therefore, energy is quantized. Now, another experiment was going on. I'm not going to talk too much about this, except for the following fact. This experiment, Heinrich Hertz, after the discovery of the electrons in the atom, he wanted to see how can he lodge the electrons and can he figure out the energy of those electrons. What he found, to his surprise, that by using light, you can, but it turned out not all light were able to do this. So this is known as the photoelectric effect. Some light can eject electrons off of a metal surface where others cannot. That frequency dependency is very puzzling. I am not going to go too much into the detail, just know that. Don't worry about it. You don't need to know any of this stuff, just that it was a problem, and Albert Einstein proposed an explanation to that problem. His explanation was as follows. In order for light or metal surface or electrons from a metal surface to have a frequency dependency in order to absorb light to leave the metal surface, Light cannot be continuous and it cannot be a wave. Light has to be made up of particles. But wait a second. So his explanation was those particles, which he called photons, they're packets of energy, the same packets of energy that Max Planck described. So he's piggybacking on the idea of Max Planck. And so when you have a high energy photon bumps into an atom, it will transfer its energy to the electron and the electron can be ejected. But wait a second. Didn't we say 100 years earlier that Thomas Young have scientific evidence that light is a wave? So how could Einstein propose that light is a particle, flow of particles? So he had to come up with an explanation. So he said light has two properties, a wave-like property and a particle-like property. He never said light is a wave, and he never said light is a particle. What he said, it behaves, it has those properties. So actually, light is neither. It's not a wave, it's not flow of particles, but instead it's a quantum vector field. What that means that under certain conditions, it's like when you shine it through narrow slits, it behaves like a wave can. If you shine it on a metal surface, it actually behaves like a particle can. So this is known as the wave-particle duality. All right. So some of you have taken chemistry before and you've heard someone say that light is both. No, please, just wipe that idea. It is not. Light is not both. It behaves like a particle. It behaves like a wave, but it's neither one. So we don't know really what it is. Not yet. All right. Now, in addition to black body radiation and the photoelectric effect was also another observed phenomena that could not be explained by classical physics, and that would be that when you subject different matter to energy, they will glow different colors. On top of this, if you were to take an atom, if you take one of those that are glowing and subject it to refraction, in other words, run it through a prism, you would actually get what's known as a line spectrum. So if we were to look at the hydrogen line spectrum, we see that we have 1, 2, 3, 4 lines of hydrogen. So these 4 lines of hydrogen, the line spectrum, what am I doing? Hold on. I circled the wrong line. Right here. There we go. These 4 lines of hydrogen, known as a line spectrum, can be observed for many other atoms. And each atom has a unique line spectrum. In other words, it was always thought that the spectrum should be continuous, but this is discontinuous. So that also adds to this phenomena of energy, light, as being discontinuous. Light is not continuous. So the first stab at explaining this was proposed or offered by Rydberg, where he said those lines can be explained, right? Since we said the wavelength describes the color, can be explained by the following equation without giving an explanation what n is. He said it's just the difference in the inverse of the square of integers multiplied by a constant, Rydberg's constant, this one right there. And he was able to actually come up with, he was able to account for all the lines in the hydrogen spectrum. Now, before we talk about an actual concrete model to explain this, I want to go back to the Rutherford model of the nuclear atom. We know that the atom contains a nucleus that is very, very, very small, and the whole mass of the atom is concentrated there, and it's positively charged, but that positive charge is neutralized by the negative charge of the electrons, where the electrons was proposed to be moving freely in the empty space. Unfortunately, there are problems with that model. All right, according to physics, and I'm going to leave it at that, moving charged particles, they give off energy. And when they do, that means they should glow. But we know that matter does not glow. All right, matter does not glow. In addition, if something is given off energy, it should lose it. And if it does, then electrons should lose all of their energy and they should crash into the nucleus, but they don't. And this is where the first attempt to explain all these phenomena together up to this point was Niels Bohr when he proposed his model of the atom. He used Planck's assumption to explain all of these phenomena in the following way. That electrons in an atom do not freely flow, but rather orbit the nucleus. So they are restricted in their movement to certain orbits, and those orbits have the same energy as the electrons. Hence, if they have the same energy as the electron can exist there as if it doesn't have any energy. Therefore, it's going to move, but it won't glow, and it won't lose any of its energy. In addition, those electrons are only permitted in these specific orbits, okay? Because they're there, they can't move anywhere else unless we can cause them to change their energy. So if you object them to an outside source of energy, you're going to cause those electrons to absorb that energy and leap to another energy level. And since that other energy level is not native to those electrons, they want to radiate that energy back and go back to their native state. By doing so, we see those lines. All right? We see those lines. And those allowed energy levels where the electrons can exist can be calculated by Planck's equation. Can be calculated by Planck's equation. So the way he proposed it as follows. So if we take an electron that exists in n equals 1, and forget about what n is right now. So let's just concentrate. Let's say it's energy level 1, 2, orbit 3, orbit 5, 4, and so on and so forth. So if you take an electron, and let me see, do I have a picture of that right there? You take an electron and expose it to an outside energy source. That electron is going to absorb energy. This electron will absorb energy and move to a higher energy level. All right, it moves up. When it moves up, it's unstable. We call that an excited state, and it wants to relax back to a lower energy orbit. When it does, it releases the energy in the form of electromagnetic radiation that we can see. For hydrogen, it does so this way. So when it relaxes back from 4 to 2, it gives us green. If it relaxes back from 5 to 2, it'll give us violet. When it relaxes back from 3 to 2, it'll give us red. And it's missing one more. Indigo, it's somewhere in here too. So that's usually how it works. And the electron cannot exist in between according to this model. That's why I said leap. Notice it can be in energy level 2, 3, 4, or 5, but it can never be in between. Therefore, the electron will undergo energy leap. It will disappear and appear at the same time between these different orbits. Okay, it can never exist. It's impossible for an electron to exist between orbits in the Bohr model. That's what's known as a quantum leap. All right, we can calculate that energy using Rydberg's equation. That's the equation, Rydberg's equation. If we take the absolute value of that change in energy, which is equivalent to energy of the photon, then we can use Planck's equation. Then we use, when we set it equal to the equation that I showed you in the beginning of this lecture, and we can relate lambda to frequency to the energy through this. So you guys need to know how to use these equations. I will give you those equations on the data sheet. And I also will give you Rydberg's constant. It's 2.18 times 10 to the negative 18 joule. And those ends that I told you in Rydberg's equation that he did not know what they were, now they're called orbits or energy levels. They're orbits or energy levels in this model. Let's look at an example. Calculate the frequency and wavelength of the n equals 3 to n equals 1 atomic transition in the hydrogen atom. So I have the following equation. I am looking for frequency and wavelength. So I know frequency, it's h nu. That means frequency equal energy of the photon over Planck's constant, which equals dE over Planck's constant. Now let me set it up. So it will be minus RH over Planck's constant. Okay, so frequency is going to equal 2.18 times 10 to the negative 18 joules times second. Divide that by 6.626 times 10 to the negative 34 joules times second. Multiply that by 1 over 1 squared, which is 1, minus 1 over 9. 3 squared, right, is 9. And this is going to give me 2.9 times 10 to the 15 per second. All right. Now, if I want to calculate lambda, then lambda equal C over frequency. So in this case, why is this doing this? I can't even write here. All right, C over frequency. So that would be, C is this one right there. So I'm going to put that number divided by this number right here, right? So it'll be 2.99 divided by 2.9 times 10 to the 15. This is 10 to the 8. So I get 104 nanometer. nanometers. Now let's look at the Bohr model. So that the Bohr model was able to predict the lines of the hydrogen emission spectra. However, it could not predict the emission spectra of other elements that were multi-electronic. For that reason, the Bohr model had to be replaced with a more sophisticated model known as the quantum mechanical model. And that's what we're going to be looking at next. So that quantum mechanical model replaced orbits with orbitals. And we need to be careful with the nomenclature. So orbitals are different from orbits. They represent a probability map that's going to show us a statistical distribution of the likelihood of finding an electron in a certain location. Okay, completely different than orbits. And as I told you many times, the best scientific model to ever hit was the quantum mechanical model in the 20th century. It revolutionized everything we know. All right, it just we have to be very careful when we look at the quantum mechanical model. So before I continue, I'm going to stop here, then we'll continue our discussion on this in the next video part.